there are two important aspects, right, for this data structure, when which one we wanted to choose, right, for any problem, right. One is the storage, how we wanted to store this data, right. So in storage there is something called a linear and non-linear. That is one, right. Based on that, like we have some data we wanted to store somewhere, right. Which one we use, we can use anyone, right. But but for our specific use case, which one we use, that depends upon how are we going to access that data. That is the next point. Now accessing is divided into further 2 points: read versus write. Okay, so now we'll talk about these four terminology, and considering these four pointers, right, each of these are very important, right. And considering these four pointer, we choose a right data structure to store. I would say to store a data, it could be an integer, a string, all that, right. For example, how we are writing through the data, right. Let's say we are, our requirement is keep on writing. There is no read functionality. Read would be only once, right, and it is on keep on writing, right. It's okay, we can just use the array list, right. And we will get into deep dive of each of these data structure. And believe me, this is very important. I know, like, you most of you already know about it, but you might see there are some of the cases that will open up the eyes for us, or maybe kind of a refresher, and that would definitely help us to choosing a data structure, right. And when we choose for a specific data use case, maybe I'll ask you as well, like which data structure you use for this particular use case, and why not other. So we will go into this mode, and that will help us to build our base stronger on this particular topic. So yeah, for write, we can just use the array list, right. And let's say the read part of it, how we are reading it, and the delete as well. I actually missed this part, right. It's more about the write, read, and the delete part of it, right. So if you wanted to delete, right, from the middle, if you wanted to write, we can use the array list, right. We keep writing it. But if you wanted to delete it from the end, yes, array list is fine. But if you wanted to delete from the middle, then what would happen? Would array list would be fine? If not, then which one? All right. And if you have a requirement, like when we wanted to keep on adding and deleting it from the end, or deleting it from the beginning, which one would be the right data structure? And what is the drawback on using other data structure? This is about the access pattern, and based on that we choose the data structure. And there is something called a search as well, right, for the linear, non-linear storage part of it. So sometimes we store the data in a linear structure. It means that is a continuous memory allocation. So there will be 1, 5, 9. These all are stored in a same memory allocation in the address space. I want to talk about that as well. I know that's little basic, but it's kind of a refresher for all of us, and that would help us to understand, and that will give us some interest as well, like why actually we are doing all that. So this is a linear data structure. All these elements are allocated in our RAM into the continuous memory allocation. Accessing from here to here is very easy because we know the address of this. Whatever the address of this, it would be kind of a +4 for integer variable, and we will be able to jump it. And that's where the array index helped us. Now there are something called a non-linear data structure, 8, 9, 12, right? Now, if we wanted to iterate through these elements, it was a continuous, we can print it. If you wanted to print it all these elements, right? And now these numbers are allocated in the RAM at some memory location somewhere, right? Now, how do we reach to these numbers from one to other? And now this is called a linear, the one which we are discussing about. This is the linear, and this is the non-linear. And there are multiple definitions of linear and non-linear as well. When we store into the form of a tree, that is also non-linear, but tree comes, this is the basic concept. That's how the tree is being defined, because all the nodes on the tree are at a different memory allocation. It's not at a continuous memory allocation like an array or like as an array list, right? And with this is a non-linear memory allocation allocated, jumping from one element to another element, printing it. We wanted to have some kind of a link if you wanted to print all these elements. Generally, in non-linear data structure, we can have access to only one number at a time. We do not want it to have another, list where we wanted to keep the address of each of these elements, right? This is something like a hash map. Actually, hash map I have too much here. Let me add the hash map in this list, right? So in fact, for this kind of a data structure storage, also we have one data structure called hash map, where all the values, all the objects are allocated in some memory allocation somewhere, and we are keeping those addresses as a part of the key in, and that's what it is, a hash map. And when we want to iterate through all the element, we go through key by key. We can go back value by value as well, but generally we have a reference to the key. We go to each of the key and we go to the value, we print it, go to the value, print it, go to the value, print it. This is one form of, another form of a nonlinear data structure, right? Another way is, we go down, we have some number like 5, 7, 3. Another form of this number is like these are allocated in some memory location, and we can have a link. As I always says that in this kind of a data structure, we always have a link to only one number at a time. Okay, one number at a time. Let's say we have access to 5. Now 5 can access 3. In 5, we will have some link where we can address 3. From 3, we can access 7. But from 5, we cannot access 7 directly. So that's why we having a link, and this kind of a data structure, there is a one kind of a data structure. Now you can see this is more like a linked list, right? There is a one node which contains the address of the another node that contains the address of the other node. Okay. Now we wanted to access, let's say there are so many numbers, we wanted to access 3 from here, right? Now in this 3, we do not have any reference to this 3. And as I always says that we can have access to only one number at a time. So we only have an address to the head of the linked list. So that's why we have to go through each of these elements one by one to see whether 3 is there, 3 is there. We have to go through one node at a time. And we are going through kind of a linear fashion in this case. But the nodes are segregated or allocated in a different memory location. But in this case, we are going through linearly. We are going through traverse to each of the node. At worst case, we will be able to traverse through each of these elements, right? And there are thousands of elements. Maybe we go through thousands of elements to search for a number. But how about if we have divided this in a form of a nonlinear data structure, if we store it? For example, let's say 3, and any number which is lesser than 3, we store it here. Any number which are greater than 3, which is store it here, right? For a simplicity, I'm not talking about basically rebalancing the tree. There is something called a rebalancing the tree. But for the simplicity, let's not talk about rebalancing the tree. It means the numbers what we are getting, we are getting in a our expected number, right? For example, positive number. For example, let's say we got a 1 again. So 1, where should 1 should go? 1 should go, 3 is lesser than this, 5 is lesser than this, then 1 can go here. And then we got 4. Right, so 4 should be greater than 3. So number 4 should go, cannot go here, right? So 4 is greater than 3. So 4, actually this 5, right? 5, the number from 3, it should be 2 actually. We have 3 number earlier, 3 to 7. So this is how we divided. 3 lesser than 3 comes to left, lesser than 3 goes to 7. If we got another 1, that should go here. If we got a number 4, the number should go, any number which is greater than 3 should go on the right. If we have a greater number, then the smaller number should go here. This is how we build a tree. Okay, and now what I was talking about, right? The access pattern, how the data structure we use, how the data structure we will build based on about access pattern. So why we are doing such a hard work here? And let's say we got some number, kind of a number called 4 or number called 5, that would need to rebalance the tree. It means 3 needs to be removed, added to here, and 4 will be added into the top because of the conflicts, because of the left and right child. So that is called rebalancing, and that is something called a medium level, intermediate level concept, which we do not get into it right now. But rebalancing also we can do, right? But why are we doing all this? Storing it into different memory location in a form of left, right, trees concept, right? Why we are doing all that? This is basically when we wanted to search for a number. This is the right part what we have did. And now we wanted to search for a number. Let's say we wanted to search for a number called 4 here, right? So we always have, as I told you in the previous time as well, we always have access to only one node at a time. So we always have access to head of this tree. and these are the left and right child of the tree, which I'm trying to cover. I'm not getting very technical part of it. I'm just trying to cover the very basic concepts so that you will have understanding why these different data structure in fact have been built. First of all, why has been built, and then we'll say why, how it is being used, right? So for 3, right, we are searching for a number called 4, right? So we can say, is this a 4? No. Can I get a number on the left of side of this tree? No, because all the left node are smaller than this. So we do not want to search, right? And we avoid searching all these numbers. It could be thousands of numbers as well, right? Now we know the 4 can be on the right of it. So we go to the right. Now we have access only to this node at a time. We do not have access to any other node. Now, is this number 4? No. Can we have a number on right of 7? No, because all the numbers of 4 is smaller than 7. So 4 we can go on the left. So let's go to the left, access to this. Is this 4? Yes. So now, how many iteration it took to check? 1, 2, and 3. Right. For your explanation, maybe I can just mention like this. So here, right, with the iteration of 3, we get a number of 4, right? Why if we have a linear data structure where we have stored in a form of this, and if the number is at the extreme end, it could be 1, 2, 3, 4, 5 iteration, but in this case we have got into the 3 iteration. When we search for all the number, we say the time complexity is O of n, right? And when we are keep on dividing by half the n number, we are keep on dividing the half of this. For example, you see this complete data structure we have divided into half for the search. We're not looking at the left side of it at all. We are just focusing on this. And further in the next iteration, we are dividing. So at every iteration, we are dividing the number by half. For example, if it is 1,000 nodes here, that first iteration itself, it would be 500, 250, 125, 75, 32, right? 16, 8, 4, 2, 1. How much maximum it would be, right? Maximum it could be a 10 iteration, I believe, right? For searching for a number, 10 iteration. Otherwise, if it is a linear structure, it could be 1,000 iteration, right? That's what it is called as a log of n. Whenever you divide a number half of every time, and there is a formula that some point of time we will see. This is a mathematical formula of AP and GP series that we have learned right in our 10th standard, 9th standard, about the arithmetic progression, geometric progression. That is a mathematical thing. So whenever you have any number which you are dividing 1 by 2, 1 by 4, 1 by 4, 1 by 8, and that gives you the formula for the log n. Okay. And that's what the time complexity you will be able to define. And that's what now you would be able to relate why we are doing, because of the access pattern. Because of the access pattern, how we are reading it, how we are writing it, how we are deleting it, whether it's a read heavy, whether it's a write heavy. Based on that, we wanted to choose which data structure we wanted to use.